In this video, we are going to talk about the concept of total internal reflection. And we're going to demonstrate this principle with the PhET bending light simulation. So here we have a laser. It is inside of glass already. So we have an index of refraction of 1.5. Why is the laser in glass? Don't worry about that so much. Just what matters is that the laser light is in glass. And then over here we have air, which has a lower index of refraction at 1.0. And we can see, as we know, we have both reflection at the boundary and refraction at the boundary. We also know that this angle of refraction is going to be bigger than the incidence angle because we're entering a faster material, air, and so the light will bend away from the normal. The new concept is this. I want to actually show the wave demonstration for this. And we can see we have some laser light here, and it's a bunched up short frequency waves. In the faster material, those waves spread out more. And we can see how much of the light gets reflected by how opaque this reflected light is. I'm going to move this laser toward the boundary. We can see as I do that, the reflected light is getting, more of the light's getting reflected. We also see that our refracted light is bending even more away from the normal and thinning out. So let me repeat that. Here, only a little bit of reflected light and not very refracted. Here, very refracted angle, more reflected light. I want to take this to the extreme now. Watch the refracted beam. I want to draw your attention to the refracted beam. As I bring the laser more and more down, we see we're approaching a point where this refracted beam is going to be at 90 degrees. And once we get there, boom, there is no more refraction. All of the light gets reflected. And if I stay at an even bigger incident angle, still all of the light gets reflected. No more transmission, no more refraction. This concept is called total internal reflection. Reflection because it bounces off, internal because the light stays in the glass, and total because all of the light stays in the glass. None of it passes through. And again, that happens, let's go back up here. Now we've got some transmitted light that happens whenever your refracted angle approaches 90 degrees. And boom, total internal reflection. I do want to say that this is like a limiting process. The refracted angle will never actually be 90 degrees. You're never going to get laser light that goes exactly to the right on this screen. It's only going to approach it. And once you get to the point where it would be 90 degrees or more, that's when you get total internal reflection. Let's look at a side-by-side diagram of this same process. So light will pass through in a straight line if it is not incident at an angle to the normal. And then as we go from left to right in this diagram, we see that our incident angle is getting more and more. Here, theta 1, we refract to a bigger angle, theta 2. Here, at this theta sub c, the refraction is exactly 90 degrees. Again, I want to emphasize no light actually is there, but that is sort of the boundary where that would happen. And we call this theta sub c the critical angle, the angle at which we are at the boundary between some refraction and then at the other side, total reflection. So let's recap. When light travels, look at the top first. Total internal reflection occurs when the refracted angle would be greater than or equal to 90 degrees. So when light travels, and this has to go from a more optically dense material to a less optically dense material. So from glass to air is the only way this is going to work, because the light has to bend away from the normal more after it transmits out. So anyways, when light travels from a more optically dense medium 1, or of refractive index N1, into a less optically dense medium 2 of refractive index N2. So in other words, N1 is bigger than N2. The refracted beam in medium 2 bends away from the normal line. That always happens. If the incidence angle theta 1 is greater than some critical angle theta sub c, then all of the light is reflected back into the medium, not just some of it, but all of it. The way to find this critical angle is to use Snell's law, where the refracted angle is 90 degrees. So it's N1 sine theta c equals N2 sine 90 degrees, and you can solve for the critical angle. I want to I borrowed some of this wording from our textbook from Atkina. I want to give some credit there. This is very useful. Fiber optic cables use this idea of total internal reflection to transmit information over vast distances at the speed of light. So if you create a cable where you can get electromagnetic waves to totally internally reflect in that material, then it'll just keep bouncing without ever escaping. And so we have a core with a very high refractive index, and then on the outside, it's wrapped in some material that has a lower refractive index. So if you send information in your light wave, and you can do that by modulating the frequency of your light wave, think like Morse code light pulses, but more complicated. If you do that, you can send information over great distances, and it's not just at the speed of electron movement or something like that, but it's the speed of light. Snell's law has total internal reflection built in. What I mean by that is sometimes you'll get a calculator error when you go to calculate the angle of refraction. And that calculator error is telling you, whoa, now there is no angle of refraction. It all internally reflects. So there it is in bullet points. So sometimes when solving Snell's law for the angle of refraction, you do everything right and your calculator says, no way, Jose, that's not going to work. When this happens, that means there is no angle of refraction. All of the light is reflected, none of it transmits. The calculator error is due to the fact that you're trying to find the sine of an angle which is greater than 1, and we all know that sine can't be greater than 1. All right, so that's it. Total internal reflection. Super cool, useful in transmitting information through fiber optic cables. Sometimes we'll be asked to look for the critical angle.